This tower stands on loose desert sand, gets hit by strong wind almost every day, and rises more than 800 meters into the sky. On paper, a structure like this should not be stable. So how does it stay standing? By the end of this video, you'll understand the exact engineering decisions that make it possible. Welcome to Loyal Engineering, where practical knowledge becomes professional skill. The Burj Khalifa is currently the tallest building in the world, but height was never the hardest part. The real challenge was keeping a slender tower stable against wind forces, weak soil, and its own weight, without overusing material or making the structure impractical to build. In this video, we'll break down the core structural system, the foundation, the wind control strategy, and the construction method engineers use to make this possible. Every solution you'll see here solves a specific real engineering problem. Let's start at the center of the building, literally. At the heart of the Burj Khalifa is a hexagonal reinforced concrete core. This core carries the building's vertical load and houses the elevator system. On its own, a core this slender relative to the building's height would be structurally unstable under wind loading. It would bend more than reinforced concrete can safely handle. The design team, led by the engineering firm Skidmore, Owings and Merrill, needed additional lateral support without adding a bulky, impractical structure around it. Their solution borrowed an idea from a completely different type of structure, the buttress walls used to reinforce dams. Wing-shaped concrete walls extend outward from the hexagonal core in 3 directions, forming a Y-shaped floor plan. These buttresses were designed so residents could live directly beside them without realizing they're a structural element. The space between buttress walls became corridors and living areas, and glass facades were added around them for unobstructed views. When wind pushes on one side of the building, the buttress walls on the opposite side resist that force and prevent the tower from bending too far. But here's where it gets technical. Concrete is strong in compression, but weak in tension. When the core bends, one side goes into tension, and that's exactly where concrete is most likely to crack. To manage this, engineers connected the buttress walls to the core with cross walls, effectively creating an I-beam-shaped cross-section at key points. An I-beam shape is one of the most tension-resistant profiles in structural engineering, which is why this detail matters so much here. Looking at the tower's exterior, you'll notice horizontal bands at certain floors that look different from the rest. These are mechanical floors. They house the electrical systems, air conditioning equipment, and water tanks that keep the building operational. No one lives on these levels. Structurally, they also help stabilize the dense network of columns that run through the tower by tying them back to the core at regular intervals. Here's a detail many engineering students don't expect. Look closely at the shape of the Burj Khalifa from above. It isn't symmetrical. Why would designers deliberately avoid symmetry on a structure this important? The answer is a phenomenon called vortex shedding. When wind flows around a tall structure, it peels off in alternating swirling patterns called vortices. These vortices create a fluctuating side-to-side force on the building. If that force happens to match the building's natural frequency of vibration, you get resonance. And resonance means the oscillations don't stay constant, they keep growing. Left unmanaged, that's a serious structural risk on a building this tall. To break this pattern, structural engineer Bill Baker and his team designed the building as a series of setbacks that spiral upward. Each tier is a slightly different shape and height than the one below it. This constantly changing profile disrupts the wind's ability to form a consistent, synchronized vortex pattern around the building. Near the very top, the setback angles change even more frequently to fight vortex shedding at that height specifically. This single architectural decision is a major reason the tower was able to grow far beyond its originally planned height, without the wind problem becoming unmanageable. Now let's go underground, because the foundation had its own serious challenge. Site investigations found no strong bedrock layer within reach beneath the site. The soil profile consisted of weaker sand and sedimentary rock. That created two problems: low load-bearing capacity and the risk of differential settlement, where different parts of the building sink at different rates and cause structural damage. The solution combined a thick, reinforced concrete raft, essentially a large slab that spreads the building's weight across a wide area, with deep bored piles beneath it. The piles don't rely on hitting hard rock. They transfer load through skin friction along their length into the surrounding soil and rock layers. At the very top of the tower sits a lightning arrestor. Given the building's height, it naturally attracts lightning strikes across a wide radius around Dubai. The system is designed to intercept a strike and channel the electrical charge down through the steel structure into grounding points at the foundation, keeping the strike from damaging the building. One more construction challenge worth knowing. Pumping concrete to extreme heights in a hot climate is difficult, because concrete can begin to set before it even reaches the pour location. The project used specially formulated high-performance concrete mixes, cooled with ice during batching, and pours were often scheduled at night when temperatures were lower. This kind of careful sequencing is why the project could maintain a consistent construction pace over several years. Now let's test what you've learned. Imagine an alternative design: a tall tower with the same hexagonal core but no buttress walls and no cross-wall connections, just the bare core resisting all the wind load alone. Pause for a second. Can you identify the engineer's mistake here? Without the buttresses and I-section connections, the core would be forced to resist bending on its own. Under strong wind loading, tensile stress on one face of the core could exceed what the reinforced concrete section can safely carry, leading to cracking and, over time, a serious loss of structural performance. The buttress system isn't a stylistic choice. It's what keeps the tensile stress within safe limits. Here's a simple way to see this principle for yourself. Take a thin ruler and hold one end firmly on a table while pushing the free end sideways. Notice how much it flexes. Now hold a second ruler against the first, connected near the base, and push again. The connected pair resists bending far more effectively. That's the same basic principle behind connecting buttress walls to the core. Multiple elements working together resist lateral force far better than one slender element alone. Before we wrap up, here's a quick checklist you can apply to your own high-rise or tall structure projects. Let's summarize. The Burj Khalifa's stability comes from a buttressed core system that manages tensile stress under wind load, a spiraling setback design that disrupts vortex shedding, and a raft and pile foundation that manages weak soil and differential settlement. The key professional lesson here is this: on a project of this scale, structural stability rarely comes from one clever idea. It comes from several coordinated systems, each solving a specific, well-understood problem. If this video improved your practical engineering knowledge, subscribe to Loyal Engineering and share it with another engineer. At Loyal Engineering, we help you build your knowledge, improve your skills, and grow your career. Knowledge, skill, career.